So the Boeing 737 class scale of a fully electric aircraft is one of the most difficult classes of aircraft to fully electrify. That's because you really need an entire power plant on the aircraft, making around 24 to 30 megawatts of power to hit that 150 to 200 passenger requirement and the range requirements, which will likely need some distributed electric propulsion and power system. You need to maintain high efficiency because you're going to have most likely going to have a much heavier system, so you have lower fuel burn, so you don't need as much fuel. To hit the environmental standards, you need to have that zero and low emission or low emissions, so your system needs to be able to compensate for that. And then you want to hit some low cost operations with that lower fuel burn. A lot of the challenges come from the dynamic environment of flight, going from sea level to 35,000 feet. And this includes vast changes in your ambient temperature and pressure, as well as throughout the flight, you have a large changes in electrical load for your system. So your system needs to be able to handle all of that while being high power density and high efficiency. Another thing with electric aircraft is you're going to have hundreds of kilowatts, if not 1 to 2 megawatts of thermal management you have to deal with. And that's not really going to be talked about here, but it is something to think about when you are thinking of electrifying a 737 class aircraft. So kind of getting the specifics of what this study looked at for the kind of budget and requirements for the aircraft. So 30 megawatts of power, of peak power during takeoff, and that translates to around 10 megawatts of power during cruise. Our mass and volume budget came from the weight of the mass of two LEAP 1B engines and a full fuel tank of jet fuel. That comes out to around 26,000 kilograms. And then the volume estimates came from a study done by Atlas Air, which you can see the diagram on the left, kind of displaying some of the volume of the different cargo components and passenger components of the 737. So if we shift things around magically, ignoring its effect on the center of the CG and center of pressure, then we end up with a volume budget of around 43,000 liters. So this is our budget we're working with when looking deeper at the aircraft power generation system. And as I mentioned before, we're proposing a solid oxide fuel cell gas turbine hybrid as the power generation. Here you can see kind of a traditional one, a traditional system layout, and this has been demonstrated before by Mitsubishi, Siemens, Westinghouse, and Rolls-Royce, I think LG also. But this system is great at achieving high efficiencies. But what it's not great at is handling the dynamic environments of flight. So the fuel cell and gas turbine have really good synergy. The turbine is able to operate off the waste heat of the fuel cell, providing it with high pressure compressor discharge. But with some of the drawbacks of this is this high temperature heat exchanger, which I'll get the laser pointer here. High temperature heat exchanger shown here, and this adds really a large thermal mass to the system, and does not allow you to quickly thermally manage the SOFC stack during flight, which ideally you'd want the SOFC to remain isothermal. And the main control of this cathode air, which is mainly thermally controlling the stack, is with this high temperature valve. So that's a lot of complexity and weight, and added to the system that's not able to really respond fast to dynamic environments. You also get some added back pressure with this recuperating heat exchanger using the turbine exhaust. So our system, our proposed system is pretty similar to the traditional SOFC hybrid shown previously with some slight changes. What's shown here is the integrated power and thermal management system. So heavily integrating both the fuel thermal management, which is being used to cool all of the power electronics, the motors and generators, and then that fuel is sent to what's shown in red here, the ESPG, on the power generation, and used to produce electricity for the aircraft. And what's shown in red is what I'll be mainly talking about today. So looking closer at that system, we can really see its resemblance to the traditional SOFC hybrid, but we've essentially removed the high temperature valves and heat exchangers and replaced them with a fuel control valve with this SOFC Combustor concept, which we are set to demonstrating this at the small scale, 1 kilowatt scale. Just to give you perspective for the aircraft, this does require megawatts of fuel cell, so 4 to 6 megawatts depending on your requirements. and efficiency targets. But this SOFC combustor is really what allows us to thermally manage the stack successfully. So I'll just kind of go through it here in this cartoon. So the fuel comes in to this manifold is sent down the SOFC anode, where it's electrochemically reacted, but not fully reacted. So you have some unspent fuel mixed with steam and maybe some other species depending on the fuel. And this anode-off gas is then combusted with the compressor discharge air, which is being warmed by that compression process. And this combustion temperature, raising the flow of this cathode air, which is around 19% oxygen, 18 to 19, depending on your off gas composition, is then sent through the cathode, and that heated up air is really what allows you to thermally manage the stack, as well as some other things that I might mention later. And then this exhaust gas is then sent to a post combustor. This post combustor is only nominally operated during high power events, so takeoff, missed approach on landing. Maybe you have some fuel cell loss of power during cruise, and you can operate this post combustor, lowering your efficiency, but able to generate more power and get a higher power density. So this post combustor just allows you to raise the power density by increasing your turbine inlet temp, allowing you to draw more load, for a given speed. What's nice about this system, it's pretty fuel flexible to a degree. Does really well with liquid natural gas, liquid ammonia, liquid hydrogen will have some caveats, and then it can work with SAF, or at least we're working to prove that. But you're gonna need some added onboard fuel processing, such as desulfurization and partial oxidation reactor. So the system sounds great, but some of the cons are it's never been fully demonstrated, as well as the SOFC durability, both thermally and structurally, really need to be investigated to be able to handle the vibrations of flight and the structural requirements that the tube needs to withstand. So quickly, the SOFC is a pretty key component of this system. So how are we modeling it? Well, so we have a pressurized test stand to be able to test these SOFCs at aircraft-like operating conditions. So we utilize that test stand to grab some data and then fit that data to our electrochemical model. To make this model flexible, we ran the model through a large range of operating conditions and then fit that model to a surrogate equation with pretty high accuracy, 0.96. The goal here was just to try to capture the performance change in the SOFC with different fuel utilizations, hydrogen percentages, operating temperatures and pressures when we're looking at the system, so we can kind of take in those effects. Now, kind of looking at the sizing, how we're estimating the mass and volume of the system, because when you're looking at range and power density, it's critical that you have at least some sort of estimate, a reliable estimate for how large your system is, because that, however large it is, you have whatever's left over for fuel, both mass and volume wise. So here's our packing strategy. We have a centralized power plant, which is made up of these SOFC tubes, the single tubes. These are packaged into these SOFC combustor submodules, and these all include their own pre-combustor and exhaust manifolds. These submodule boxes are then placed into these pressure vessels, which I might call cigar tubes just based out of habit. But this pressure vessel or cigar tube is doing two things. It's holding the pressure as well as acting as some sort of manifold, controlling where the compressor discharge air goes, as well as the exhaust, the fuel inlet, and the electrical bus. And then these pressure vessels are packaged together depending on your sizing constraints, your length and height you can fit into, and then placed into an aircraft. So this SOFC sizing estimation, or just calculating the mass and volume for a given operating point, is not too difficult, but finding the optimal mass is not so straightforward. So there's some key sizing parameters, being the total electrochemical active area. So based on your system power requirements, you're going to have a varying how much SOFC you need. your maximum operating pressure determined by your gas turbine, and maybe some other system trade studies. Your tube geometry, which is depending on your manufacturing capabilities to be able to hit the tube performance for a different size of tubes, which you're familiar with SOFCs. The size of the tube plays a large role in how much performance you can get, as well as factors of safety and what material you're using for the vessel. So you have all these parameters that are likely determined by the system. But for each of these combinations of the operating parameters, there is going to be an optimal mass and volume for this SOFC packaging strategy. So what I propose is that for each of these conditions, there's going to be an optimal number of tubes per one of these SOFC modules, an optimal number of each of these pressure vessels or cigar tubes, and all of these are constrained by your sizing requirements, and then you're going to have an optimal operating temperature for your vessel. Because as you can see here, your yield strength is heavily dependent on temperature. So the higher temperature you operate at, you need a thinner insulation layer, but you're going to need a thicker vessel because your yield strength has degraded. So you have this kind of complex problem where there's a lot of things pulling in different directions. And you also, with this problem, you produce a lot of local minima when just varying parameters. So utilizing an algorithm that can find the true global minima is necessary. So we utilize a genetic algorithm. So for a given pressure ratio, a total stack active area, and tube geometry, it'll optimize how many tubes per module, or for one of those box modules, which is constrained by your maximum diameter, the number of cigar tubes constrained by your max length, as well as your operating temperature, which affects your total vessel diameter and insulation thickness. But using this complex, geometrical stress model and thermal resistance model in an entire system model is not ideal, because you can get pretty computationally expensive, and it takes a long time if you're wanting to do full system trade studies to have to do this genetic optimization each time. So what we did is kind of create a reduced order model for this sizing estimation. So ran the model, the optimizer, the genetic optimizer through a long range of pressure ratios, total stack active areas, and SOFC tube diameter, as you can see here, and found the optimal mass. And then fit that basically large table of data to a couple of equations, depending on what the component. But the base form of the equation can be seen here. And with this fit, we have pretty good R-squared values, good enough for a full system trade study to try to take in the behavior of this SOFC packaging strategy. Just for reference, this mass does include the mass of that pressure vessel, insulation, the flanges. As you get more cigar tubes, you're going to need more flanges, so you get a penalty there. Each of the boxes and manifolds for the combustor and exhaust. The turbogenerator sizing estimations is much easier, or was much simpler. We just took a bunch of existing turboshaft engines, mainly helicopter engines, found their mass and volume, and related that to its design mass flow rate to generate some correlation curves. To kind of end the kind of sizing talk, we'll look at the different fuel comparison. So the four fuels that I'll be comparing here are liquid hydrogen, liquid natural gas, liquid ammonia, and SAF. And just looking at their mass-specific and volume-specific lower heating values, you can already see some of the trade-offs. Liquid hydrogen having the gold standard of lower heating values, mass-specific, but having terrible volume-specific lower heating value. LNG and SAF kind of being closer to the middle, and then liquid ammonia having the lowest lower heating value, mass-specific, and in the middle of volume-specific lower heating value. So this likely just tells us from looking at the charts that our hydrogen system is most likely going to be volume limited, just based off of that lower energy you get per liter, as well as you can look at the densities here and see the trade-offs. Ammonia will likely be mass limited. So we're going to fill up our entire mass budget just because we hit lower energy per kilogram with a very high density fuel. The fuel also has effect on your your electrical component performance. So the liquid hydrogen is very cold, cryogenic, is going to allow your electrical components to have very high power densities and efficiencies. And as the temperature of your fuel goes up, your power density and efficiency is going to drop. Some other caveats for mainly LNG and ammonia is they both involve a thermal decomposition of the fuel, which is endothermic for both of these fuels. And that's a good thing because it allows you to use the waste heat of the SOFC to kind of thermally manage the SOFC stack, as well as taking the lower heating value of the fuel and converting it to hydrogen, which is a much higher heating value of the fuel. So you get a gain in efficiency using these fuels because of their added chemical reaction benefits. So kind of keeping the system constant, power requirement and budget wise, and varying just which fuel we're using, we can look at the comparison shown here. So on the left, we have the propulsion specific power, x-axis versus the propulsion efficiency. And these propulsion efficiencies and specific power includes the efficiencies of the ESPG, as well as the efficiencies of the propulsion system. So the ducted fans, propellers, power electronics, motors as well. So this is kind of a total combined value. You can see the Boeing 737 MAX for reference has a much higher power density but lower efficiency than our proposed system. Then our systems hang in the higher efficiency, lower power density range. Methane, as I mentioned before, methane and ammonia are able to achieve the higher efficiencies due to that endothermic cracking of the fuel to be able to produce a higher heating value fuel for a lower fuel flow rate. Whereas hydrogen, you don't have any of those endothermic reactions to help benefit the thermal management of the stack. When looking at flight time, it's better to look at this energy density chart, where it really represents or really shows you have a higher energy density, you're most likely going to have a higher flight time. With LNG having kind of the best of both worlds of relatively high density and good mass and volume specific lower heating values compared to liquid hydrogen, which you get a much lower flight time, shown here only around 2.5 hours compared to the 7.6. And that's because you're heavily volume limited. With a very low density of liquid hydrogen, you just fill up all the volume budget you have way before you reach the mass. And that's actually why you see this higher energy density here. So this ammonia system is very heavy. You fill up your entirety of the mass, so that full 26,000 kilograms per how much energy you're generating. So you get the higher flight time due to the higher efficiencies, but you have that much lower energy density just due to how heavy the system is. So now I'll vary some of the key components and see their effect on the system range and other performance. So 3 fuels are shown here: liquid ammonia, LNG, and liquid hydrogen. And what I varied is the SOFC peak power. So if you're familiar with the SOFC world, a watts per centimeter squared or area specific power is pretty common way to describe the performance of the SOFC. And varying this, we can see how obviously as you get a better SOFC, you're going to get better system performance. But I really wanted to try to quantify that. And from each of these charts, we really want to hit around the 0.8 to that 1 watts per centimeter squared range, range to be able to get the full benefits of system capabilities. Here you can also see kind of a mass limited and volume limited curves for each, where hydrogen is heavily volume limited, and ammonia is mass limited up to a certain SOFC volume. What's essentially happening here is that as your SOFC gets better performance, you're able to have less of it and get more room for fuel. So that's why you see an increase in range as your SOFC gets better. So this power was held constant. So this is all for the same cruise power requirement, as well as these charts as well. The same cruise power requirement of 10 megawatts total. So what happens if you just vary the size of the SOFC stack while keeping the SOFC performance constant, or the peak power constant? So what you see here on the x-axis is the SOFC total electrochemical active area. So as you increase this, you get more tubes, allowing you to operate at a higher voltage, raising the efficiency of the system, which you can see here on the right. But as you get more tubes, you have a higher volume system, a higher mass system, taking away from how much fuel you can carry. But you can see here that there is an optimal point where you're at a high operating voltage, giving you a highest efficiency, where you're not taking away from how much fuel you have, because the higher efficiency, lower fuel burn, but less fuel you can carry with the bigger stack. The reason we're seeing kind of these square root shaped graphs is just due to the performance or the nature of SOFC power curve shown here, where it's a parabolic shape. For a given power output, you have two solutions. So at a lower voltage here and a higher voltage here with the better range. Now just varying some of the gas turbine components. So isentropic efficiencies for both the turbine and compressor are shown here on the left, and how they affect range. So as they increase, you're going to get a better performing gas turbine. Your compressor requires less work. Your turbine is able to generate more power for a given heat input. As well as, higher efficiency is going to be able to get you better range, because you're essentially keeping the gas turbine the same size, just increasing its performance. And then looking at the gas turbine pressure ratio, we see there's an optimal pressure ratio of somewhere between 15 and 25. This is likely going to be, system dependent, but for this given system, it's between 15 and 25. And this is due to having a higher pressure ratio. It means you're going to get a lot more work required out of your compressor for the same heat input to your turbine, or energy input to your turbine. But also there's some competing effect. There's another effect from the SOFC. So as you increase your SOFC pressure, you're going to get higher SOFC performance. But your SOFC vessel itself is going to get heavier with the higher pressure ratio due to it needing to be thicker. So due to these kind of fighting effects, we see an optimal pressure ratio for this given system might be around that 15 to 25 range. So through these trade studies that I've shown here and done a lot more, not shown, there's a lot of terms, or there's a lot of knobs to turn to try to optimize this system. And a lot of it's probably going to be operational requirement specific or vehicle dependent on what your actual mission is and what you're trying to accomplish with this electrified system. Your gas turbine design mass flow is a big key component. It allows you to thermally manage the SOFC stack, as well as maintain a acceptable oxygen percentage of the cathode exit. Your gas turbine pressure ratio as well is a big component, as I mentioned before, affecting both the total mass of your SOFC combustor system as well as system performance. One thing that I didn't mention here is that pressure does have effects on the thermal decomposition of both of the ammonia and methane. Ammonia, it actually gets slightly better at increased pressure. Performing the methane at higher pressure does decrease your conversion, as well as SOFC performance typically gets better with increased pressure. Your turbine inlet temperature is a big component to your peak power density of your system. So how much energy you're able to extract from your turbine is heavily dependent on this turbine inlet temperature, as well as shown with the previous charts and their effect on range, the SOFC performance, just individual on a tube basis. So I think I'm doing okay on time. We also did a degradation study. So looking at the degradation of the SOFC2 performance, as well as the gas turbine, and seeing how that affects your total system efficiency. So we work with a company, Special Power Sources, and they supply us with tubular SOFCs, and they typically see a SOFC degradation rate around the 0.5 to 0.75 percent degradation per 1,000 hours. So this range here in the plot shown on the right goes from 0 to 1, and we can see its effect on total operation efficiency over a 20,000 hour lifetime. And at least from this analysis with LNG, excuse me, we're only seeing around a 2% drop in efficiency, worst case scenario, over the entire life of the aircraft. And basically what's happening is just as the SOFC performance degrades, you're having to operate at a lower voltage for the same power output, dropping your efficiency, but not by too much. And, engineers doing cost estimation is always a dangerous game, but having, just taking a rough guess for jet fuel, which is probably underpriced today, and a price for LNG per kilowatt hour, this increase in efficiency over the lifetime of the aircraft can result in around $24 million in savings, likely more with the higher cost of jet fuel. So that at least based on this study, the degradation is not playing a huge role if we can maintain the SOFC degradation rate per 1,000 hours to around 0 to 1%. So to kind of conclude, with this study and a lot of the analysis we've done, we think that the SOFC hybrid system is a viable solution for future electric commercial aircraft, as well as just power needing systems. If you want a high efficiency power generation method, you can get roughly, double the current state of the art in the aviation industry. The SOFC hybrid is fuel flexible to a degree. I would like to dig deeper into what SAF looks like with this system. But you need to come up with, clever ways, if you want to optimize the system, clever ways of where you're putting these external fuel processing and thermal decomposition reactors. One caveat about having this centralized power plant on your aircraft is, you're going to have a very large power distribution network. So you're going to need to pump a lot of power around the aircraft, which is also going to increase the weight. And the weight of that really wasn't considered in this study. We were just looking at the electrical storage and power generation section. The SOFC Combustor provides a great way of thermally managing the SOFC stack and is fuel agnostic, as long as you can, maintain that pre-combustion temperature. In future work, we'd really like to continue to increase the fidelity of our system component models, as well as full system models, and include as much experimental work in our modeling as possible. I'd like to acknowledge ARPA-E REACH program and the Department of Energy for supporting a lot of this work, as well as NASA, where we just got funded with a ULI titled Clean, mentioned by Dr. Roberts earlier in the presentation.